Okay, we're going to revisit these complex numbers then. All right, so let's go down here. A complex number. Okay, is a number that can be expressed in the standard form. So it's just that z equals a plus bi. I don't know, which may not.
So a complex number is just a formula.
Well, it's not really, because a complex number, if we look at this chart here, okay, a complex number are the imaginary numbers as well as the real numbers. Those are still considered complex.
So it's just a number.
It's just a number.
Okay, so all numbers are complex numbers.
All numbers are complex numbers. You got it.
So it's just another way of saying real numbers.
Right. So, but when we've talked about real numbers in the past, right, we've had whole numbers, we have integers, we have rational and irrational numbers.
So we're just adding another layer to that.
Yes, we're just adding another layer to the real numbers. And that layer is, so we're adding imaginary, right, because they have the I in them. But in doing so, we're saying, well, actually, all of these, the imaginary and the real, fall under the scope of what we call complex numbers.
Okay, that makes a little bit more sense.
Okay.
So you had your list, you had like rational numbers and irrational numbers.
Uh-huh.
And you have real numbers, right? Or is real numbers above that?
Real numbers was above that.
Okay, so you have real numbers, and then basically above that you just have complex numbers.
Yeah.
So would irrational numbers still fall under that complex numbers, or is that?
Yep. Irrational still under there.
Okay.
Because irrational was under, like, was with real. So under real, we had rational and irrational.
Okay.
So
basically, any number you can dream up is going to be a complex number.
Correct.
Okay.
So we have complex.
Just a term referring to literally any number.
Yes.
Okay.
Literally any number. Because we'd have complex would break off into imaginary and then real. And then real would break off into irrational. Yes.
And then you get into your integers and all of that.
Right. You got it. And then you have integers, whole numbers, natural numbers, all those.
Okay.
So does that make sense then?
That makes more sense.
Okay, perfect. So yeah, it's just this all-encompassing term that we use, complex. And then, so when we have a real number though, it's when our b is equal to 0. So that means we don't ever see the imaginary part of it. We just see the real component.
So that a plus bi is a formula for what?
That's a formula for like real numbers, like when b is 0. So it ends up being a plus 0i, which is equal to just a, the real number. Because in the complex, there's a real and there's an imaginary component. To every number. Yep, to every number. So, yeah, so in the imaginary, let's see if I change here. Okay, in the imaginary side, it's that same formula. It's a plus bi, but b is not equal to 0. So here is not. So that means we have to have some part to the imaginary. So
if b is not equal to 0, it's going to be an imaginary number.
Correct.
If it is equal to 0, then it's going to be a real number.
Correct. You got it. If b is equal to 0, it's real. Because when we simplify this, like the square, or let negative 15, we could write out as negative 15 plus 0i. But we don't write it like that. Like we write, it's the same way as saying $15, right? We could write it like this, but we don't. Like we usually just write the dollar sign and the 15. We don't need the zeros to hold that place. We can talk about it as $15.
So all that is basically writing the proper number.
Yeah. Yes, this is more like the proper form of writing negative 15. That's one way to think about it.
So is the formula a plus bi, is that to test to see if the number is imaginary or real, or is it just something that just is?
That is just the formula for a complex number, because every number has a real component. The a, okay, is the real component, and the bi is the imaginary component. So that's just how a number is, yes. And so, but again, when we don't have that component, we don't ever write it. Like it just takes too much. But because we don't have an imaginary component, then the number is real. Like it's something we can, we can usually see and touch and count, 15 or 27 or 23 or 3/5 of a pizza. Like we can see it, we can count it. Whereas when we get to the imaginary part, if it has an imaginary component that we like added to it, then we put it in that imaginary component because it has a real and an imaginary, or it can have.
Can we quickly rerun through what imaginary number is, just so I remember?
Yeah. So when we have the square root of -1 or any negative number, that equals an imaginary number.
So I'm just confused about like what that means. Like what do you mean it's imaginary? Like it has a value, so why is it imaginary?
Right. It does have a value, but and people do like work on those things and they create these really cool fractals and stuff that you can see like watch some YouTube videos of and things. But for us to calculate it, it's something that's way beyond where our level is, so we don't need to calculate and deal with any of that. So
it's just saving a lot of math.
it's just saving a lot of math at this point. Like just saying like, okay, this is just as far as we need to go with it, kind of, is that it's I. That
So
it's just an imaginary number.
It's not necessarily that the number doesn't exist. It's just saying you don't know how to find this yet, so just write this in for now.
Absolutely. Yeah. It's not that it doesn't exist.
That's
it's just
confusing me because I thought imaginary meant like it doesn't have a solution. I'm like, it clearly does. You can find it.
right. Yes, it's just beyond our scope and realm right now.
Okay. So
Yes.
it's saying instead of doing a half hour worth of math to solve one problem, just put this.
Yes. Mhm.
That
Mhm.
makes sense.
Okay. And so then when we have something, so like when we have something like the square root of -8, we can say, oh, well, then that's the same thing as the square root of -1 times the square root of 8, which is like, okay, this, I pulled that out because I'm like, okay, well, that's my I. I got to get the negative out. Then I can deal with the square root of 8. And so then we just, again, like we tack when we find this, because 8 is 2 cubed. So it's 2 times the square root, or 2 times the square root of 2 is that square root of 8. But we've got to put the I in there. So it's 2I times the square root of 2. Because we can't forget our I. We pulled it out for that time. Just to say like, hey, I don't know how to do the square root of a negative number. I'm going to take that out. We'll put an I there, and we're going to move on. Okay, perfect. How about that? You're not sure? Okay.
Just keep going and hopefully I get it.
And keep going and hopefully you get it. Okay.
So, which part are you confused about?
That's the thing.
The complex numbers or the imaginary numbers?
I don't know. It just seems all weird and confusing.
Seems all weird and confusing. Okay.
Basically,
How about
what I can tell you, because that's what I had to do, you don't know anything about a number, so just relearn it this way.
there you go. How did it go with graphing?
It's the same thing until you got to the 3D graphing.
Okay, until I got to the 3D graphing.
Well, it was like, well, you said there was like another axis or something like that, and at that point, I was like, above example 1.
Okay, so there's not another axis, but when we're finding the absolute value, is that what you're thinking of? Because it's the distance. So because we're looking at a point, previously when we've talked about absolute value, it's always been on a number line. How far is a number away from 0? So like 3 is 3 places away, and -4 is 4 places away. That's a terrible drawing. Thank you for laughing. 4 places away from 0. But now that we're graphing a point on a plane, it's the shortest distance from the origin to that point is the diagonal, or the hypotenuse. Is like if you think about right triangles, right? Because this would make a right triangle. And so then the shortest distance from the origin to that point would be the hypotenuse of that triangle. And so if you know anything about, if you remember anything, not that you know, but if you remember, then the way to find a hypotenuse is a squared plus b squared equals c squared. Okay, so that's where this idea, this formula comes from, is because we're looking at the side lengths of this right triangle in order to get the hypotenuse, which is the distance from at that point to 0, or it's the hypotenuse of the triangle it makes. Because no matter where we have a point, if I have a point down here, it's still going to form a right triangle, and then I'm going to have to find that hypotenuse to find the distance.
So it makes a little more sense now that I understand what a complex number is. So
Okay.
it's just, instead of writing 3, it has to be 3 plus 0i.
Yeah.
Because you just have to write, instead of just writing 3, you have to write out the proper-ish form, I guess you could say.
Yeah.
And put it into the formula.
Yeah, that would be in complex number form.
And then the z is just how far it is to the origin, the straight line.
Well, z is any number. So like in this case, z would equal -4 plus 0i, so z would equal -4. Z is the letter that, like real numbers, is the R symbol.
Yeah.
So z is the, in this case, is the what we're using as well.
Z is the symbol for
complex.
complex.
Yes.
Okay. So Z
Yeah.
is not a variable. It's more of a, well, it is kind of.
It's a little both. Yeah. So, because in this formula, I like it, in this one it is, but we're always using z to represent the complex number.
Okay.
Yes.
So, like when you see the R, you know that it means real number. And
Yes.
when you see the Z, just know that it just means number, basically.
Yes.
Any complex number.
Yeah.
Okay.
So then if we look at, then I'm going to go down here to where we were graphing it to look at this graphing. So this is the same thing as 4, okay, minus 1i.
Yeah,
because it's a negative I. Right. So if I were to graph it, I would go on my real numbers, I would go over 4, 1, 2, 3, 4, and I would go down 1. So that's where I graphed it.
Your real number takes, so is your real number A? Would it be the
A value is the real number.
And then anything beside the I, or I guess B is the imaginary. So
B is the imaginary.
Take the place of your X and Y.
Those just take the place of your X and Y. Yeah. And so then the -17, the square root of 17 is your absolute value. It's your distance from 0 to that point. So that line is -17. Or square root of 17.
So to do that math, do they start, so if they ask you to do a problem in the book, all you're going to get is 4 minus I and ask to solve, right?
Right. So in this case, it says graph and find the absolute value. Not to solve, but we're finding the absolute value. Okay. So in this case, we had to plug it into this formula.
So you're always coming back to that.
Oh. There are other ways that we can, just like any other problem with any number, we can do different things with it. So this is how we find the absolute value of a complex number. But we can add we can add complex numbers, and we can multiply complex numbers. We can subtract them. Just because it's a number. So this is just one way we can do something with a complex number.
So when you're trying to find this absolute value, you always have to. But if it's just a number, why do you have to use the square root? Why can't you just?
Okay. So, so again, we have.
Or is that just referring to graphically? Any other time?
Anytime you want to find the absolute value, you have to use the square root formula. Because, so taking it back to like, this is the hypotenuse of a right triangle. So we know a squared plus b squared equals c squared. C squared is the hypotenuse. So we have to find the square root of this. So the square root of a squared plus b squared is going to give me c, my distance. Look at these two. It's what we already know. It's just using a complex number. Because it's a complex, we don't have a separate, like necessarily, like we separated them on this axis, right? This is our A value. because it's the real number value. This is our B value. Because that's how we graphed it on a complex way.
Like this because B is not equal to 0. But if B is equal to 0 and there's no imaginary number,
yeah. Absolutely. If B was equal to 0 and there was no imaginary number, it would just be 4. Yes.
So because there is an imaginary number side of it, then you have to do it like this.
Yeah, sure.
Okay, that was what was
Mm-hmm.
So if B is equal to 0, meaning that it's just 4,
Mm-hmm.
then it's like we've always done it, just how far away from 0 it is.
Yes.
But if it's got something with the imaginary, then you have to do it with the square root.
Mm-hmm.
Okay.
Yeah. So this is why this is 4. A is 4 here, and B is -1.
Yeah.
So that's why, that's where those numbers came from in the formula. Yep. Mm-hmm.
So when you say square root of 17, that's not obviously it's not 17 squared, 17 like away, like there's only one.
Right, like if we actually put that in a calculator, the square root of 17, we'd get out a weird decimal number. But again, we don't need to do all that work. So the square root of 17 is actually 4.123105626. But who wants to do all that work? We just leave it. It's kind of like with pi. When we have math and we get to like leave pi in the problem, we get to leave the square root in the problem. So we have less work we have to do.
It's basically, it is only like, if you count the squares on the graph, it is only about 4-ish away. But it's,
yeah.
It wants an exact value, but you can't really guesstimate an exact value.
Right.
And instead of writing all the decimals, it's just easier to write square root of 17.
Mm-hmm. You got it. Okay. So do you want to look at adding and subtracting complex numbers then?
Yes.
Or do we want to try to graph another one? And
Can I try?
Yeah, the absolute value? Yeah.
So like that second example.
Uh-huh.
So like where do you start with math?
Well, so let's graph it first.
Oh.
Maybe.
So it would be 2 on the real number axis, or -2.
Okay.
And you're going to go up 3, or down 3.
Down 3. 1, 2, 3. Okay. So I'm going to go ahead and draw this line because this is, I'm going to put those values in there. -2, and this is -3, because that's going to give you your A and your B. Okay, so I'm going to go ahead and label them for you. Okay, so then to find the absolute value, we go back to this formula. So it's going to be the square root of.
Which side of the formula though? You use the whole thing or just the inside 2 circles?
Oh, okay, so we're finding the absolute value of this number.
Oh yeah, because that's one number.
Yeah, that's one number. So that's going to equal.
So that's already.
We just.
So that's left side of that z equals.
Uh-huh.
That's already there.
That's already there. Mm-hmm.
Okay. So then you just have to put in a squared b squared. So it'd be -2 squared plus -3 squared.
You got it.
Or is it -3i?
Nope. Nope. No squared. There's no I in there, right? Like if you look here, there is no I. We're just pulling out the A and the B. We don't care that it's imaginary.
Okay. So then you solve it?
Mm-hmm.
So then technically, shouldn't that square root part of it be behind the 3? So like it's written as an actual algebra equation, or is it not like that?
Shouldn't the square root part be behind the 3? Oh, you mean like over here?
Yeah.
Yeah.
Like shouldn't this piece be moved up like that so that it would read -2?
Yeah. If that. Uh-huh.
Or is that not? Do you not solve it like that?
No, it's the same way. It's just putting it in, if that's confusing, like putting it in there. So this equals. You're saying like writing it like this?
Yeah. And then do you have to solve it like an algebra problem?
Yeah. So it doesn't matter, like as long as you have an equal sign, like this equals, you can, just like when we write 4 plus 6 equals 10, it's the same as doing 4 plus 6 equals 10.
I just didn't know if they were independent from each other or that they had to stick together.
Nope, they are, yeah, so they are independent, but they also do go together. It's like you're writing the same sentence a different way, so we can follow your flow of thinking. So it's okay if you,
It's okay if they're both.
yes.
Okay. So then -2 squared is going to be +4.
Mm-hmm.
Positive 9.
+9, good. So then I can go this way now if I want, because I got.
Add the 13.
Okay, so we have the square root of 13, which cannot be simplified, right? So you're done.
Is that your final answer?
Yes, it is, as I try to move my board. Yep, that's your final answer.
So you really, after you plotted the point, you really don't need that -2 -3i.
Mm-mm. And I mean, like, and you don't have to plot it to even solve it either. But we needed to, I mean, I wanted a way for us to get some extra practice in of graphing. But yeah, you wouldn't even have to graph it in order to find your absolute value. You just have to use the formula.
So you're not solving it like an algebra problem to find a variable. It's not like that.
Nope. Mm-mm. Okay. That probably sounded very loud on the video there. I'm sorry, I was taking a drink of water. Okay, so then let's look at adding and subtracting some complex numbers, because they're just like adding. I mean, like, I know it seems really weird, but it's just like adding like terms. You add the real component. So in this first one, 3 plus 5 is what we did. Yeah, you're just adding the same things. And then the 2i and the minus 4i. Ooh, I like it. Yes. That's really good. So 3 plus 2i plus 5 minus 4i. Yeah, so you stack them on top and you're just adding vertical columns. 2 plus -4, is -2i. And then 3 plus 5 is? Yeah, that's a good way to think about it, just like stacking them. I like it.
So it's literally just addition.
Yeah. Now, with the minus, right, we do need to distribute this in order to make it more helpful. Like, especially if you're going to stack it like this, we could change this to be 5 minus 3i plus and distribute that negative. So it's going to be -2 minus 6i.
So you're still adding, you just have to
Yeah.
distribute.
Yeah, but if you just distribute that, then you'll be set.
You don't have to distribute the both, it's just whichever one it's in front of.
Yeah, just because we're subtracting this number. So we distribute to all the parts inside that number, like always. And then you could stack them. So I'm going to bring the other part down here, -2 minus 6i to stack. So I'm adding these quantities. So -3 plus -6 is, so -9i. And then 5 plus -2 is?
No,
3.
So question, do you have to distribute or could you just subtract? Because if you subtracted -3 from 6, you're still going to get 9, right?
Yeah.
So you don't have to distribute, you can just stack them and subtract.
Yes, if you remember to, yes.
You don't remember to not like borrow, right?
Right, like
You just have to make it a negative anyway, so borrow.
-2 plus 6i. So the kicker here is remembering because that it's -3i minus 6i, like bringing over, looking at the 6, versus here where we had -3 plus -6. Like plus is kind of automatically in our brain. So like -3 and -6 is a -9. Where here you just can't forget that you're subtracting. But yes, you could also do it that way.
So you just distributed it just so you could add because adding is easier than subtracting.
Yes, generally for most people. Awesome.
Not that it's a necessary step, it's just that it's easier to do it that way.
Yeah. Good. All right, so let's look then at multiplication.
So that's adding and subtracting.
Yeah, adding and subtracting, we combine like terms. Okay, and then the last
We
page.
just have to remember all
There's just the one formula for the absolute value.
That's the only
That's
formula.
the only formula. And the other, you're doing the same things you've always done. It's just feels awkward at first because there's two parts to the number.
It's just the same thing you've always done, just written different.
Yeah, same thing you've always done, just written different. So like, because like this one with moving on to multiplication, we're still using the distributive property or the FOIL method that we've always known. We've always done that. Okay, the only new part is that we also have to contend with this -1 thing if we have it. If we get an I squared out of it, which we're going to at some point. Okay, so yes. Okay, so let's look at this one. So here we have one term, which is called a monomial, times a two-term number, or a two-part complex number. So this is where we would distribute. This one, we have a two-term number times another two-term number, so two binomials, and that's when we would FOIL. So just looking at the two. Yep, it depends on what you have. If you can distribute, distribute. If you need a FOIL, then you FOIL. Okay, that was supposed to delete my things. Okay, so let's start with this first one. We've got the 5i we're going to distribute. So 5i times 3i. 5 times 3 is? Well, 5i times 3. So,
that would just be 15i.
yep, 15i, just like we've done with x and x squared and different things, same thing. You just treat it as a variable. So then 5i times 2i. So 10i squared. Okay, but we know I squared is equal to -1. No, I is equal to the square root of -1.
So when you square it, it just takes away the square root.
Yeah, when you square it, it takes away the square root. So in this case, this is the same thing as saying, well, this is 15i plus 10 times -1, which is just -10.
So anytime, is it safe to say anytime there's I squared, you just change the sign in front of the number?
It is totally safe to say that you just change the sign in front of the number and you get rid of the I squared.
Even if it's, so you say you started with 15i minus 10i squared, would it change to positive 10?
Indeed it would, because a negative times a negative is a positive.
So just change the sign.
Just change the sign. Yep. Get rid of the I squared and make it a negative, or change the sign actually would be better. Now, and the one flaw here is that it's not in that correct form, right? Like the standard form is the real number first. So we would just change it to be -10, put my real number first, plus the imaginary part.
So you just have to flip it.
Yeah, I just flip it to get it in standard form. Okay, so now let's go FOIL on this one. So 4 times 2 is 8. 4 times 3i is you got it. Okay, so that was the first and the outside. Now let's do the inside. So -2i times 2 would be -4i, I think I heard. Okay. Okay, good. And so I'm going to circle this because it's the negative. So -2i times 3i.
-6i squared.
You got it.
And then you just change that to, do you have to add like terms and stuff?
Would you have to add like terms and stuff?
So then you could say it's 8 plus 8, so 12 plus 8i plus 6.
Got it. Ooh, now you have more like terms. Oh, because you got rid of the I squared.
Yeah, so then it's just 6 plus 8i.
You got it.
And then it's already in the correct format.
It's already in the correct format.
Okay, that's easy. I guess what was confusing was understanding what the complex number was.
Okay.
Once you get that,
Yeah. A complex, because that's it. A complex number, it's complex. It has two parts to it. Like in English, you guys talk about compound and complex, compound, complex sentences. Okay, so same thing. In a complex sentence, it has more parts to it. Okay.
So I have a question. You can just tell me it doesn't. You just tell me no if you don't
Okay.
want to answer it. So if a complex number is just any number just written differently, that's only when it's b is equal to 0, right? Because if it has an imaginary part, then it's no longer just like 3. It's 3 and something.
Right. So if it has an imaginary part, like the only time we actually see generally the complex number, or like we will only ever see an imaginary number written as a complex number. Well, that's not true either, because it can be pure imaginary, where it just has an imaginary part, it has no real part. Only if a number has a real part and an imaginary part do we see it written as a complex number.
So if it has a real part and an imaginary part, what does that like mean? Like what? Like how would you ever get that?
Um,
Or is that just something best left to?
yeah, I can't think of a way to answer that question right now, because we do get imaginary parts, like when we were doing,
But those are
um,
pure imaginary.
but they were pure imaginary. Yeah, we were getting pure imaginary parts. So when do you get a complex number? We haven't gotten there yet.
Because to me it seems like if you had a math problem and you got a number like that, you might break the matrix. Like that wormhole's gonna open up and suck you out of the universe because it's not working like that.
Right, and you kind of might feel like that. But yeah, no, so let's table that question. Because we have gotten, what we have been working with has been pure, like real numbers
Real numbers.
or pure imaginary numbers.
So
This is our first time working with both together in that complex form. And so they're still imaginary, like they're just not pure imaginary because they have two parts. They have the imaginary and the real. So they're imaginary, but we also call them complex because complex encompasses everything.
so you can't. It's not really a set number.
Hmm.
If you have a complex.
Right.
So you couldn't convert it to like a hard value. It's just
Right.
is what it is.
Mm-hmm. Mm-hmm. Okay.
Like you couldn't count that number.
No, you cannot count this number.
It's just is.
And that's why it's more imaginary. It's like it's not a number that we can count.
It's not a number that you can get.
Yes. Yes. Okay, so I'm going to bypass the sum of the square stuff. That's kind of the least important in my opinion. And I want to see how we did with the simplifying of the powers of I.
So it's basically just knowing, like it's a kind of a shortcut, right?
It is a shortcut. It's definitely a shortcut. It is a matter of knowing like how powers work. So I to the power of 1 is going to give us I.
It's just I.
Mm-hmm.
And then I squared, you're going to get negative 1.
Uh-huh.
And you have I cubed, you get negative I. You have I to the 4th, it's just going to be 1.
Right, and this is the awesome part. Because I to the 4th is 1, and when we multiply anything by 1, it doesn't change anything. And 1 to the power, any power at all, if we 1 to the 100th power, is still 1 times 1 times 1 times 1 times 1 times 1. It's still just 1. It doesn't matter what power it is, which is why we can divide it by 4.
I have a question now.
Uh-huh.
I to the 1st is just, it's not I times 1, right? It's just I times I.
I to the 1st is literally just I. Like I have one I.
Oh, yeah. I was thinking in terms of multiplying by 1, that it's not.
Yeah, it's not multiplying by 1. It's just saying. Okay. Okay. So yeah, so that's the thing. So it's the remainder that is the necessity part. Okay.
Can you explain what we did though? So if you have I to the 59th.
Okay, so I divided it by 4 to see how many of these I was going to get out.
How many ones?
How many groups of 4 i's am I going to get? Okay, and so that says, hey, you're going to get 14 groups of I to the 4th, because those are all just ones. So I can pull all those out. And then I have an I to the 3. My remainder of 3 says I'm going to have I to the power of 3. And once I know that, I know, well, hey, I to the power of 3 is actually equal to a negative I. So 1 to the 14th is 1 times negative I is just equal to negative I. Or 1 to the 14th is equal to 1. Yeah. And 1 times negative I equals negative I. So you could totally disregard this number, whatever. You could disregard all this. It's just 1. It's all going to cancel. It's all going to equal 1.
So then when you do it, you divide it, you get whatever left over. It's always going to be 1 through 3.
It's always going to be 1 through 3.
And then you just have to write I, negative 1 or negative I.
Yep.
And that's your final simplified answer.
That is your final simplified answer. Yep. Because like I to the 7th, if we did this, right, would equal I times I times I times I times I times I times I. 1, 2, 3, 4, 5, 6, 7. Okay. So this. Yep. And so this one is equal to the square root of negative 1, the square root of negative 1, the square root of negative 1. Well, a square root and a square root is equal to, well, is equal to a negative 1, right? Right, because the 2 squared, so this is going to be negative 1. And then we still have the square root of negative 1, which we just call I. We never, that's like keeping it. So this would be 1 times negative 1 times I, which is the same thing as negative I. Which would have, if we took that, that's just explaining the math of the shortcut. You got it. But I didn't want to, you don't want to do that 59 times, right? That would suck. Yeah. That's just explaining the math of the shortcut. Okay. So then try your,
just go back and do the homework.
Go back and do the homework again tonight. And see where we get.